So this time we have a proper session by Professor Mikhail Wira. So please start.
Okay. So I wanted to start by just clearing up a point of confusion from last time. So it was pointed out that in the definition of the this Z sigma that I defined, there was some confusion about whether it should be sigma or sigma inverse. So I believe that if I've done it correctly now, the correct statement is that sigma k, so the line that begins at position sigma k, will connect to position k at the top of the lattice. So basically all that changed is previously this sigma here was actually in front of this k. So the way you can see this actually is every single line in this picture. So there are n lines here. So our line begins with an index I and ends with index j. And it should be that the subscript that gets associated both to the I and the j should be the same for any given line. So if we go along the bottom here, where I have this collection of i's, somewhere in here is going to be I sigma 1. And furthermore, it will happen precisely at position sigma 1. And that line then has to connect with this line here. So it has to terminate with j sigma 1. And so then you can see that what's written here is actually correct, at least in the case k equals 1. So hopefully that clears that up. All right, so I'll get started with some of these examples that I sort of laid out in the lecture last time. So most of these examples will be quite simple, but actually towards the end, I'll give some new material. So I'll state the theorem that I didn't state in the previous lecture, which is sometimes called the color blindness lemma or color blindness theorem. And then we'll give an example of this color blindness property, which will actually be important in the coming lecture tomorrow. All right, so let's get started with examples. So the first one was just a little warm-up. So these are the problems. So number one was to basically compute the number of non-trivial vertices in the model that we're looking at. So compute an, the number of, let's say, non-vanishing vertices in the, I'll call it the UQ SLN plus 1 model, since that's what it is. And then explicitly tabulate the weights in the SL3 case. So that would be the n equals 2 case. Okay, so very simple counting problem. So last time we saw there's 3 types of vertices in this model. So this is the first one. So that's where I have all the same color around the 4 edges of the vertex. And so clearly k here can take n plus 1 possible values. So the number of these is just n plus 1. Then I had these more interesting vertices where, let's say, I have I here and j here. And maybe let's assume that the colors cross. And so for these ones, it's a little more complicated. So here we're assuming that that I is not equal to j. So clearly for I, there are n plus 1 possible choices. And then once you have chosen I, there are n remaining choices for j. So that gives n plus 1 times n. And then for the remaining the remaining vertex. So that's where the colors kind of bounce off each other, if you like. Now this one, and the enumeration of that is exactly the same. So n plus 1 times n. So we just have to add up all of these, and so this gives that an is equal to n plus 1 times 2n plus 1. Okay, and if you go ahead and work these out, so indeed A1 is 6, just being 6 vertex model. A2, which is the case we're interested in, is 15. And then the next one is 28, and so on. All right, so we have 15 vertices to tabulate. So I'll just copy one of these. And I'll put them into columns. So we'll have, each column will have 3. And so I'm going to need this another 4 times. So this is one of the advantages of doing things on iPad. You can easily do this. So. Okay, so how is the grouping going to work? So in the very first column, that will correspond with this first type here, where all the colors are the same. So there are 3 possibilities. So I can have all zeros, I can have all ones, I can have all twos. Okay, and the weight for all of these is just identically 1. And then following cases can happen. So these next 2 columns are going to be where the colors cross each other. So I can have these 3. So in all of these cases, the first index at the bottom is smaller than the second index. And then we have the flip, the mirror image of those. And these weights are given as follows. So the first column is of the form Q times BZ. So recall that I'll give it afterwards, actually. So the second one is BZ. And then the final 2 columns will be the so-called C vertices. These are the ones where the colors sort of bounce off each other. And so I have these types. And then their mirror images. And the weights of those are going to be of the form, this is 1 minus Q BZ, and this one is 1 minus BZ. Okay, so just to remind you of the definitions. So all of these vertices have x assigned to the sort of left line and y assigned to the right. And I'm assuming that z is defined as y divided by x. And b of z is just this rational function 1 minus z over 1 minus qz. So this is the model that you get, sometimes called 15 vertex model. So if you ever see this name, then you know now what this model is. And as I said, it's quite useful for us to think of this in terms of families of colored lattice paths. So quite often we will not draw the zero color. We can just think of it as being empty space, but it's useful to draw the other ones. So maybe I'll just do that very quickly. So maybe ones can we can agree that they'll always be red. So we get something like this. And then, I don't know, maybe we'll make the 2's to be greens. Okay, so that's the model that one has in the SL3 case. So please feel free to interrupt with questions at any stage. But if not, I'll go on immediately to the next example. Okay, so problem number 2 was to prove the unitarity equation. This one is slightly more involved, so we're going to have to do a little bit of work. So let's start out by recalling what we need to prove actually. So we defined last time this quantity U, I1, I2, and J1, J2. And that was the following partition function. So I have a line that goes straight, and then I have another one that kind of loops over it and then loops back. And at the bottom, I have I1, I2. At the top, I have J1, J2. And we need to pay attention to the spectral parameters. That's going to be of significance. So I'll choose this to be X and the second one to be Y. And it's very important to note that once you go through the first vertex, they actually switch positions relative to each other. So this line will still be Y, but this will be X. And this definitely plays a role in what follows. All right, so we have to prove that this is equal basically to the identity. So it should be indicator that I1 is equal to J1 and indicator that I2 is equal to J2. All right, so the way we can do this is by a sort of case-by-case analysis. Equivalently, one can represent this thing in terms of matrices and then just prove the thing directly on the matrix, but it's entirely equivalent. So let's actually just do this kind of case-by-case analysis. So the first thing to consider is the case where I1 and I2 are both equal. So in the case I1 is equal to I2 is equal to K, say, where K can be any color in the set 0 up to N. So in this case, by conservation of colors, we must have that J1 is equal to J2 is equal to K. If that's not true, then the partition function will vanish. And that's just because of conservation. Whatever comes into the lattice from below has to exit from the top. Okay, so must have this or else the object vanishes. Okay, and furthermore, when it is satisfied, so when all of the indices are equal to K, one gets the following picture. So when all equal to K, we're going to have this. I have 2 Ks coming in from below and 2 Ks going out from above. And notice that then fixes entirely what happens on those 2 internal edges inside of the lattice. Particularly, normally you're supposed to sum over those, but here, again, they will both be forced to be equal to K. Otherwise, the object is going to vanish. So in this case, you actually just have a product of 2 vertices, both of which are completely frozen. And both of those vertices have weight 1. So indeed, in this case, the answer is equal to 1. Okay? So at least in the case so when I1 is equal to I2, the claim holds. Okay, so that was the easy part. Now we have to work a little bit harder. So in the case I1 say is equal to I, and I2 is equal to J, with I not equal to J. Sorry, was there a question? I heard some noise. Yeah, I don't think so. Okay, so in this case, yeah. So basically, you're looking at the situation where the two colors that come in from below are now different. So once again, it's going to be true that the two colors that exit, so these ones, they will have to either be of the form ij or ji, otherwise the object is going to vanish again. So in this situation, there are two subcases to consider. So A is when say J1 is equal to I and J2 is equal to J. And in that case, we actually have to prove that we get 1. And the second case is where J1 is equal to J and J2 is equal to I. And in this situation, we're supposed to have 0. Okay. So let's do that. So now for case A, we're going to have the following. So right, so at the bottom I have I and J. That was the assumption that we made. And we're going to assume in this case that we have I and J going out at the top. And so actually, if you think about what happens with these internal edges, there's two choices for them. So they can either be of the form ij or ji. So we're actually going to have a sum of two of these things. Right, and the first one I'll write as ij, and the second one as ji. And let's just remind ourselves of the spectral parameters. They look like this. Okay, so now you have to use the explicit form of the weights. So I did the computation. So I'll just write down what the answer was, and people can check, hopefully, that the working is correct. So basically, I'm reading it in the following order now. So I'll do this vertex first, then this one, then this one, and then this one. Okay, so I should have this. Times this. And then plus the diagram on the right, which is actually of the form q to the indicator that I is less than j, b of y over x, and then q to the indicator that I is greater than j, b of x over y. So suddenly that's it's not obvious that that's going to equal 1. But there is something here that helps to simplify a little bit, which is that here I have basically both indicators for the relative sign of I and j. So one of them has to be true and one of them has to be false. So I will always have a power of q coming from those. And then there is an identity which kind of proves the statement immediately. So the following identity holds. So if I take 1 minus alpha. So alpha is just a parameter here. And then 1 minus alpha b of x over y. So this first product is corresponding with these terms here. And then, as I said, you're certain to have q, and then just b of y over x, and b of x over y. And this thing actually factorizes. So if you explicitly compute it, you get x minus y squared, alpha minus q, and alpha minus 1. So we don't care too much about what it is, actually. Oh, I'm sorry, I've missed a minus 1 here. The minus 1 is important because we want to prove that all of that is equal to 1. So if you subtract off 1, you better get something which is equal to 0. So you get this. And so indeed, substituting the two possible values for alpha. So these things are representing alpha here. So it's either equal to 1 or q, and in both cases, that gives you a root of this numerator. So indeed, this quantity is equal to 1, regardless of what happens with this. Okay, and then the remaining case. Case B. Now, once again, there's going to be two of these diagrams to consider. So once again, ij enters from below, but now I have ji going out from above. And indeed, this is supposed to vanish because the index that appears here does not match with the index that appears here.
Can I ask a question?
Yes.
Can you go back a bit?
How far?
It's just here. So what are you computing just on the last line?
So I would like to show that the identity, basically I would like to show that all of this stuff here is equal to 1.
Yep.
But you can see that it's a little bit strange because these exponents of q, these will always give you q no matter what. But basically, these ones, they're going to be different depending on whether I is smaller than or bigger than j. So it's actually two equations that needs to be checked. And rather than check both of them manually, I just came up with this identity here that checks both of them in one go.
Wow. Okay. All right.
It's just some trick. Yeah. Okay. So we'll see something similar actually for this case we're looking at here.
Michael, could you please
Yes.
recall the definition of B, please?
Yeah. So B was here.
Ah, yeah, thanks.
Yeah, where Z should always be the basically the ratio of the right parameter divided by the left parameter. Actually, it doesn't make too much difference how you define the ratio as long as you're consistent in your choice. All right. Yeah. So this is the case we're looking at now. So again, I'll just work out all of the weights, and I'm reading it in the same order as before. So I have 1 minus q, the indicator that I is less than j, b of y over x. and q to the indicator of I less than j, b of x over y, and then plus q to the indicator that I is less than j, b of y over x, and finally 1 minus q, indicator that I is greater than j, b of x over y. All right, so in this case, no immediate simplification happening. There is a common factor of q to the indicator that I is less than j. But basically, we would like to show that this is equal to 0, irrespective of the relative sign of I and j. And once again, there is an identity that that allows you to do that in one go, which I'll write here. So it's of the form 1 minus alpha b of y over x times b of x over y plus b of y over x, and then 1 minus beta, the new parameter, b of x over y. And if I copy that correctly, you get something that looks very similar to the previous answer. So all of these factors are the same, actually. But what changes is you now get 1 plus q minus alpha minus beta. And so indeed, alpha and beta are either of the form 1q or q1. And in both cases, this is going to vanish. So indeed, this is going to be equal to 0. Yeah, I have to say that even something as simple as this pretty innocent-looking equation is already rather non-trivial. So it really shows you that there's a lot going on beneath the surface in these models that one can easily take for granted.
So the two identities you used, are they useful more generally for other values of alpha or alpha and beta?
It's a very good question. I've actually never seen them before, so I literally just wrote them down for the purpose of proving these relations. Yeah, I feel that there's probably even more elegant proof than I have given here.
Actually, isn't it true that there's a relation for B of Z itself? That B of Z plus B of Z inverse is 1 plus Q B of Z times B of Z inverse.
Yeah, there should be something like this. I agree.
You put alpha and beta to 0 in the equation you just wrote.
Yep.
You get that. And that's enough.
Right. Yeah. Yep. Thank you. Yep. Okay. So let's move on. So problem number 3 was to check the Yang-Baxter equation. So it was just in the 6-vertex model case, and a particular component of the Yang-Baxter. So check the Yang-Baxter equation for the case I1, I2, I3, J1, J2, J3 being equal to 1, 1, 0, 1, 0, 1. Okay, so this is a situation where one side of the Yang-Baxter equation has just one term. So in this case, the left-hand side, which we denoted using this L, is going to look like this. So I'll have following picture. So according to the conventions that we set up, these three indices here should be read from left to right across the bottom. And then these three indices should be read in the opposite direction, although for this example, it doesn't actually matter. So that's what we have. And so one can see now that looking at this first vertex, okay, so let's just draw the orientation arrows. It has two ones that enter it, and so therefore by conservation, it has to have two ones that exit at these edges here. And once that happens, it actually freezes the rest of the picture. Because indeed, if one looks at the next vertex, there is a single one that enters from the left and a 0 that enters from below. I already have a 1 that exits from the right, so this must therefore be a 0. And so that completely freezes the picture. And just to remind you of the spectral parameters, I'm using X, Y, Z. Slightly maybe bad choice to use Z because Z was previously Y over X, but I'll do it nevertheless. So this is what we get. All right, so the vertex that has all ones, that has weight 1, so we can actually ignore it. So let's do this one next. It depends on the ratio of Z and X. So that one is of the form 1 minus Z over X and 1 minus Q Z over X. And then the remaining vertex is going to be of this type. Okay. And then for the right-hand side, it's a little more complicated. So this time the picture goes the other way. So I'm going to have this now. And it's very important that the indices have to match on both sides. So I'm still going to have exactly the same boundary conditions as I had on the left-hand side. But what changes now is the
trivial identity, Michael.
Sorry?
It's the same picture as above.
Oh, thank you. Okay. It's not going to be very interesting. Yeah. Okay. Thank you very much. Okay. So what changes here are the internal edges. All right. So let's start with this vertex here. Okay. So it has a 1 and a 0 that enter it. So actually, there's two possibilities for the outgoing states. So either they can be 0, 1 or 1, 0. So we might as well just make two copies of this picture a priori. No, that's the wrong picture. Okay, so let's make a choice here. So maybe 1, 0. And this can be 0, 1. And again, once you fix what happens with that first vertex, it freezes everything else. So this vertex here has got all 1s around it, so this will be forced to be a 1. And then finally, in this case, you'll have a 0. So now we've got to work out the weight of those two pictures using the same recipe as before. And if you go ahead and do it, you get the following. So in my notes, I've actually done it the other way around. So this is 1 minus Z over Y. One minus Q Z over Y. One minus Q times Z over X over 1 minus Q Z over X. And then finally 1 minus q y over x. And the other one is a little bit simpler because one of these vertices has weight 1. So this time we only get 2 terms. I get 1 minus q z over y, 1 minus q z over y, and then 1 minus y over x. I divide by 1 minus q y over x. Okay, so I will not do the explicit calculation, but you see it's a non-trivial identity. So this is saying that the sum of these two rational functions will be equal to this rational function up here. And if you go ahead and check it, you'll find that this is a true identity. All right. So that's probably a good point to pause and see if there are any questions, because I'm about to go on to the this color blindness lemma. Okay.
An important point here is that there is a total order on your set S of possible indices. Are there
Yes.
other models where you have maybe partially ordered sets or cyclically ordered sets for these indices? And that's still integrable?
I have to admit that I don't know the answer to that question. I would assume not, but someone in the audience may know differently. Yeah, I certainly don't. I can't, off the top of my head, think of example where you have such. I mean, now that I think of it, there is something called the ZN clock model, which may be closer to the spirit of your question. So that's a model that has a kind of inbuilt cyclicity in the states. But yeah, I haven't really studied that model, or yeah, so I'm not really qualified to answer the question.
Thanks.
Yeah. Okay, so now I will look at this this color blindness, this lemma. Before I do that, as a warm-up, I will first give the sort of most general statement of stochasticity. So I kind of hinted at it very quickly the end of the last lecture, but I'll state it more carefully now. All right, so we'll need one small definition in what follows. So we've basically already seen traces of this definition. So in many of these weights, one has to keep track of this relative sign of I and J, which one is bigger. So that suggests that underlying all of this, one cares about basically inversions. So if you think of your reading, maybe you'll have a general partition function now, so a general permutation, and you're going to read the indices, say, along the bottom, and you might want to keep track of the total number of inversions that you have in a vector. So that's kind of why we need to introduce inversions. So this is just a definition. Or we will write the following quantity. So inv sub c, which is associated to a vector of length n. And so this thing is basically just working out all inversions such that the two elements that participate in an inversion are at least equal to c. So I will have This is the cardinality of all pairs a less than b, such that Ka is greater than Kb, which is at least equal to C. And actually, we'll only need 2 cases of this. So, and what follows, we only consider C equals 0 when this restriction is totally redundant in that case, and also C is equal to 1. All right, so now let me give the, so this is, I guess, the most general version of stochasticity.
Sorry, I'm not sure I understood what C is. Is C the difference between 2 Ks, or it's the value of the minimum of the Ks?
It's the minimum of the case. Yeah. Yeah. Well, okay. Maybe I'll give an example, then it will be clear. So suppose I have something like 0, 1, 2, 2, 0, 1, 0, something like this. Right? So you can either count inv of 0, which is going to be counting all pairs such that the first element is bigger than the second. All right. So for example, this would be an inversion, or 2, 0 would be another inversion, or 2, 1. So you have to count all of them. But if you put inv of 1, basically you don't care about inversions with 0. So inv of 1 would not keep track of, say, 2 with 0. Is it clear?
You can delete all the numbers strictly less than C in the sequence, and then you just compute inv of that sequence?
That's correct. Yeah.
Okay.
So the reason we're going to need that, so inv of 0, I'm going to use basically in the statement of, so we had 2 versions of stochasticity last time. So stochastic property where you sum over the states along the top of the lattice, and also sort of reverse stochasticity where you sum along the bottom. And the statement where you sum along the bottom, you've got some Q inversions that you have to keep track of. Now, the inversion statistic that shows up there is going to be inv of 0. But then when we come to color blindness, the state 0 is going to be special compared with the rest. I want to think of all of the other colors 1 up to n as being sort of grouped together, and I want to think of 0 as being separate. So that's the reason for this extra definition. Okay. So I'll just say this is the most general version of stochasticity. All right, so there were two statements. So if I fix I1 to IN, that lives along the bottom of the lattice, then I have that by summing over all j's, j1 up to jn of z sigma, this is equal to 1 for all I. So we saw that one last time. And then the sort of the partner statement is the following. So here I will fix j1 up to jn. So these live along the top of the lattice. And so in this case, so there's some normalization here, which is q to the minus inv of 0 of j sigma 1 up to j sigma n. So don't worry too much about the sigmas here. So the reason why the sigmas are showing up, let's just go back to our picture. Okay, so basically what I'm doing here is taking this vector here in this vector here, and I'm just reading them across and keeping track of the inversions. And because the top vector has sigma built into the definition, that's why sigma is showing up here. So we get this. So there's overall Q factor here, and then I have a sum over I1 up to IN, due to the inversions sub 0 of I1 up to IN, and then just Z sigma. And that again is equal to 1 for all J's. Okay, so the proof of these, I'm not going to give the proof. It's pretty elementary. So once you know how to prove these statements for a single vertex, which basically we looked at last time, you know that your Z sigma, you can take sigma and now take some reduced word decomposition of it. So you will reduce it into a product of simple transpositions. And each simple transposition is just a single vertex in the vertex model we're looking at. So you can literally just one by one apply stochasticity to each vertex in that chain, and in this way prove the statement in general. So it's very simple inductive proof. Okay, so the reason why I wanted to give, first of all, the most general version of these stochasticity statements is it kind of provides a nice contrast to the color blindness lemma that I'm about to state. So once you see them written in this form, color blindness sort of looks quite natural as well. All right, so let's move on to the, so this will be the color blindness lemma. So for that, we're going to need one piece of notation, which is the following.
Sir, can I ask a question?
Yes.
Could you please repeat the induction step in the proof of the previous proposition? Like,
yep, that's fine. Yep. So, in general, we have, so Z sigma, what is it really? So it's just a permutation graph. It's just representing your permutation as a bipartite graph. And every single vertex that you have inside of your bipartite graph, you can actually think of this as being, a single vertex in the model that we started with. So, for example, I may have something like this. I don't know if it's a good example, but it's maybe quite difficult to see with the last one I drew. Okay, so every single vertex here corresponds to a simple transposition. So you need to have some order in which you read this. But basically for this example, I could start with this vertex here. And so basically I first use the stochasticity to sort of get rid of this vertex. So if you think of it, this vertex here will have some state that lives at the top and another one that lives here. And in stochasticity, you're supposed to sum over everything that happens at the top. So by summing over those two top edges, this vertex is supposed to have weight 1, irrespective of what comes in from these two edges at the base. So just by that fact, you can sort of remove it. So it goes away. And then what you're left with is a sum over these sort of dotted pieces that remain. So these two here. Okay, so this strand we can forget about because well, this is basically just going to be a Kronecker delta, so it will not play any role. But then you see you've reduced your your original permutation, which has a certain number of inversions in it, and you've precisely reduced the number of inversions by 1. So you'll have fewer simple transpositions. And then you can repeat this for the remaining graph. So this is now also a, let's say, Z rho, where the difference between rho and the sigma that you started with is just a single transposition.
Okay.
So was that clear? Yeah.
Yeah. So just to clarify, so the induction parameter is the length with which you can write the permutation.
Yeah, the induction on the length of the permutation. That's correct.
Okay. Thank you. Thank you.
Okay. So yeah, colorblindness lemma. So we will need the following notation. So define K star, which will be equal to 0 if K is equal to 0, and it will be equal to 1 if K is greater than or equal to 1. Okay, and so this holds for all K in our indexing set 0 up to n. So you can think of K star as being precisely a colorblind projection. So if you have, if K is equal to 0, then the projection does nothing. And if K is equal to any of the actual colors, then you project onto the color 1. Okay, so we will use this. And obviously, we will use the similar kind of notation for vectors of integers. So if I have a vector and I apply star to it, then I'm just applying star to each of the components. Okay, so here is the statement. So fix I1 up to IN that lives in 0 up to n to the n. And I will assume, so this will be such that if I take its colorblind projection, so if I apply star to each of those, I'm going to assume that this is equal to another vector, capital I1 up to capital IN. And that one lives in this colorless set. So just 0, 1 to the n. Okay, so the original vector lives in the colored model, and this capitalized vector lives in the colorblind projection. So equivalently, this will live in the 6-vertex model, whereas this one lives in the colored model. Okay. So having fixed that, the claim is the following. So if I sum, so I again perform a sum of j's, but in the statement of stochasticity, we have a free sum over the j's. So we sum over all possible j's in our indexing set. But here there will be a restriction. So the restriction will be, so it's the sum of a j's such that when I take the colorblind projection of j's, that's equal to some other vector, capital J1 up to capital Jn. Okay, so we're also fixing, so this is also something that we're given, J1 up to Jn. So hopefully it's clear. It's no longer a free sum. It's a sum over all possible ways to permute the colors in the original model, but such that when you take the colorblind projection, it's equal to some vector, which you're given ahead of time. And so the claim is, if I compute such a sum, I get the following. So I get another Z sigma, so for the same permutation as I started with, but this is now completely colorblind. So in particular, these i's and j's, they're just zeros and ones. So maybe I should also say in the statement of the thing, so we're also fixing a vector j1 up to jn, which lives in 0, 1 to the n. Okay, so it's perhaps not so intuitively clear what's going on here. So I will do an example in a moment, which will hopefully make it clear what's actually happening. But you can see that it's very similar to stochasticity. So in stochasticity, you have this this free sum over the j's. You don't impose any restriction whatsoever. Whereas in this particular statement here, you're sort of still freely summing over the colors 1 up to n, but you're fixing some positions where you definitely have zeros. And so this makes a difference then to computing the object. And at the end of doing that, you get a partition function that just lives in the 6-vertex model. So in particular, so I can just write it here. So this statement relates sum of colored partition functions to a single, say, black and white partition function.
So here you're going from n colors to 2 colors. Can you do a slightly more general thing where you go from n colors to m colors with m strictly less than n?
Yes, absolutely. You can do that as well. Yes. So basically, when you perform these kind of projections, another way to think of it is, so in the statement I gave here, I'm really symmetrizing the colors 1 up to n, and 0 is special. So actually, you can do quite versatile things. So you can symmetrize blocks of colors. The only constraint is the blocks of colors have to be contiguous. So you have to have, colors that are like nearest neighbors, and then you can symmetrize over those. And then they all sort of collapse into a single color. So there's actually quite a few versions of the statement here, including the one that you said. But I just gave this version because it's a bit more elementary.
And is there a way to go in the other direction from a small number of colors to a larger number of colors? You would need to choose the weights appropriately, I guess, for the larger number of colors.
Yeah, I mean, you can, in general, if you have a partition function in the 6-vertex model, you can always reverse this procedure and write it as a sum over colored partition functions. And the way to do that is completely algorithmic. Yes, so you can go in the other direction. But I should say that in most practical applications that we've seen, it's usually the projection that is the interesting part, because usually when you're dealing with computing quantities in these higher rank models, you usually care about being able to convert it to SL2 type model where you can actually solve stuff. So you can go both ways, but it seems that going one way is more useful than the other. So. All right. Right, so this was, I guess, statement A for color blindness. And as you will guess, there is something very, very similar. If you sort of, instead of summing over the outgoing states, you sum over the incoming states. All right, so this time we'll fix the vector I1 up to IN that lives in 0, 1 to the n. And also fix a vector j1 up to jn such that its colorblind projection is equal to some vector j1 up to jn. Okay. So in that case, oh, I forgot there's a Q inversion that I will need. So this time you get inversions, but with a subscript 1. So it's precisely the situation where you just throw out the zeros from your vectors in order to compute the inversion statistic. So q to the minus inv 1, j sigma 1 up to j sigma n. And then I have a sum over i's, I1 up to in, such that the projection is equal to this vector of i's here. And inside of the sum, I have q to the inv 1, I1 up to in. And then just z sigma. Oops. Okay, so that's the left-hand side, and it's equal to the same right-hand side as before. So just z sigma in the 6-vertex model. Okay. So that's color blindness, and yeah, you can sort of think of it as being, you have your original model that has the colors 0 through to n, and you can sort of project out as many of those as you want. So the situation we're looking at here is where you project down to just 2 colors, 0 and 1. And in fact, if you project all the way down to just 1 color, then that's just actually a statement of stochasticity. So really, all of these statements belong to sort of one family of theorems. Because if you think about it, in the case where I project onto a single color, let's say everything gets projected onto 0, then Z sigma will just have all zeros coming in and all zeros going out. And in that case, it's trivially equal to 1. So stochasticity is just part of this family of statements. All right. So I'm almost done. I wanted to just conclude with a simple example, but it's actually an example that we're going to need in the talk tomorrow. So here it is. So I'll just write it as a claim. So the following quantities are equal. So here is quantity number 1. So I'm going to draw my my partition functions in a slightly more conventional way now. So this will be my my quantity, and I will now again sort of change conventions slightly. I will agree that the horizontal lines here will be x1 and x2, and the vertical lines will be y1, y2, y3, and y4. So this is going to be the quantity that we're going to use, and I'm going to need actually 4 copies, even 5 copies of it. So let me just do that now. Okay. All right, so I'm going to put now some boundary conditions here. So at this stage, I'm just setting up the permutation graph in question and the spectral parameters. But now we actually have to put our incoming colors and our outgoing colors. And I'll use a little bit of color for doing that. So path of color 1 will be in red as previously, and a path of color 2 will be in green. And then I'm going to have all zeros at the base here. And I'll have zeros here. These will both be zeros. And then by conservation, I have to have a single 1 going out. So in this picture, I'll put the 1 here. And in this picture, I'll put the 2 here. All right, so that's the first partition function. I'm going to add to it another partition function. So that one will have the same incoming state here, for 1 and 2. But what will change will be the positions where the 1 and the 2 exit. So they will just switch places, like this. So that's quantity number 1, the sum of those two partition functions. And quantity number 2, a little bit different. So there I'll fix what happens along the top. So that will always be of this form. And likewise, all of these are just zeros. But now we're going to sum over the left incoming states. And there's going to be two possibilities there. So either I have a 1 and a 2, or I have a 2 and a 1. And there's going to be a Q factor that gets associated to this one. So it's this plus this. The claim is that those two sums of partition functions are actually equal. All right, so here, again, you're summing over the states at the top, keeping the positions where the zeros are fixed, but you're summing over the ways of, basically the two possible ways for 1 and 2 to exit. So symmetrizing over 1s and 2s. And likewise here, I'm fixing the top outgoing states, but I'm now performing a Q symmetrization over the left incoming states. All right, so those two things are equal, and the way that you prove this is simply by noticing that both quantities 1 and 2 are just colorblind. So indeed, in case number 1, this is precisely a situation where you fix all of your incoming edges. They're fixed in both of these diagrams, but you sum over the outgoing edges in such a way that you hold positions of the zeros fixed, and you sum over the remaining colors. So that's precisely the scenario where you have color blindness, which means that basically in these pictures, I can now just replace all of the 2s by 1s, and then it will be equal to the original object. So basically this object number 1 is equal to this now, where I have just 1 here and a 1 here, and a 0 here, a 1 here, a 0, and a 1. I'll copy this, maybe zoom out a little bit so that it's clear. So maybe this can be quantity number 3. Okay, so the claim is that quantity number 1 is equal to quantity number 3. And likewise, quantity number 2 is also equal to quantity number 3. And that again is just color blindness. And it's the second version of color blindness. It's the one that has this Q symmetrization showing up. So you go ahead and work out the powers of Q that we have in this case. So actually, this power of Q that comes from the outgoing states, the J's, there's actually no inversions there because here the 1 appears before the 2, and I don't care about zeros. So 1 appearing before 2 means I have actually no Q inversion. But when it comes to computing this object here, in the first case, as I read the labels in this direction, the 2 does indeed appear before the 1, so that will give me a factor of Q. But in the second case, there is no power of Q. And so by the previous lemma, both of those quantities are equal to 3 and therefore equal in their own right. Okay, so that's probably everything I wanted to say today. So yeah, if there are any questions, please ask.
So this is going back to Sanjay's question about reversing the colors. I mean, going from lower number of colors to higher number of colors. I'm not so sure you can do it, right? Otherwise, I mean, for example, in these colored stochastic models, you usually get the projection as a projection of Markov processes from higher colors to lower colors exactly by this color blindness. But you cannot go backwards. If there's some integrability, then you can build it somehow, but not in a trivial way. I don't think coloring works backwards. Is that?
Well, I mean, okay, of course it depends. One has to be more precise about what it really means to reverse this process. But certainly, just with the example that's on the screen right now, you can start either from 1 or 2 and show that it's equal to 3. Sure. Or indeed, you could start with 3 and then write it as so. In this sense, I mean that it's reversible. Okay. I can take any partition function in the 6-vertex model, and I can always perform this kind of symmetrization over like a model with more colors. I can always do that.
Sure. But that is the same kind of coloring. You're still taking more colors and coloring. I mean, I thought what you were kind of saying is that look at the left configuration in 1, for example. You cannot compute its weight from, I mean, its weight alone from using the reverse coloring, right? I mean, you need to sum over things to get. I mean, you can.
Yeah. No, okay. Then I think I've understood that. Yeah. So it's indeed true that I can take linear combinations of colored objects and get a single uncolored object.
Right.
It's not true that I can take a linear combination of uncolored objects to get a colored one. Yeah. So it's a kind of many-to-one mapping that. Yeah. So in that sense, it's not reversible.
Yeah. Thanks.
Is there any other questions or comments? Yes.
I think it's the same question again, but from the point of view of solutions of a Yang-Baxter equation. So say you know the 6-vertex solution of a Yang-Baxter equation. Is there a way of splitting it into colors in some sort of systematic way to get solutions of the Yang-Baxter equation with colors? And is this way unique? Because you have a very well-defined splitting into colors.
Yeah, I think the answer is no, probably for the reason just discussed. So, I mean, ideally, what you really would want is a correspondence where you take like a sum of just 6-vertex Yang-Baxter type pictures and convert it, say, into a single colored picture. And to the best of my knowledge, there's really no way of doing this. Yeah, so I don't know of any procedure that allows you to start from SL2 and get SL3, for example.
So it feels a bit like higher spin, but it's not at all the same thing, right? Because higher spin, it would be really to stack up 6 vertex on top of one another, and right.
Absolutely. So higher spin is another matter entirely. So there is really systematic procedure, which is just the fusion procedure that allows you to construct the higher spin representations. But yeah, to the best of my knowledge, that doesn't exist for higher rank models. Any sort of analog of that.
Other questions?
Maybe it's worth adding. So in terms of like checking Yang-Baxter equation for the higher rank models, so it's actually sufficient just to prove it for SL3. And once you prove for SL3, all of the other cases just repetitions of the same equations. So yeah, so in that sense, it's not like the procedure is going to go on forever. It has a definite end, but I still don't know how to go, say, from SL2 to SL3.
Okay, good. So let's thank speaker again. Thank you very much.
Thank you.